Graphical understanding of minimizing misclassification rate. In the previous lecture, we saw about the approach of minimizing misclassification rate and how to draw the right decision boundary. What did we learn? We learned that if we have two classes C1 and C2, to which we have to assign the input variable x, what will it do? If this is our input region space of x, this will be divided into two regions, R1 and R2 by our model, and this boundary is called the decision boundary. What will this decision boundary do? It will divide x into two regions, R1 and R2, where the point in R1 they are to be marked as class C1, and points in R2 these will be marked as class C2. So this is the whole idea, and we also solved this and we understood what was a finalization. After learning all these, we understood that in order to minimize the misclassification rate, we have to assign each x into that class which has the higher posterior ck given x. That is, if there are k classes, each class is called by k equal to 1 to k, then for each of those classes you have to identify the posterior p of ck given x. This is your posterior. You have to identify the posterior, and whichever class has the highest value of posterior, you have to assign to that class. Then we discussed that when you do this, you can consider it as a decision boundary which will put points into either class C1 or C2. In this lecture, let us see a graphical understanding of this. So what this graphical understanding will do, it will give a conceptual logical idea for you. So it will make more sense for you once you understand it graphically. That is, for now you understood it mathematically. In the next step, when you understand it graphically, the whole thing would be easier for you to imagine, right? That's why I'm specifically putting one lecture for graphical understanding. Let me show you in a graph. Let's say this is your probability and this is your x. Okay, this is your x. This is the probability up to 1. Okay, from 0. Let us say you have two classes C1 and C2. Okay, C1 and C2, and you are assigning it into C1 and C2 based on whether P of x C1 is higher or P of x C2 is higher. So we already discussed that in order to find whether x C1 is higher, you have to actually find P of C1 given x, and in order to find x C2, you have to find P of C2 given x. Okay. So why am I considering x C1 here? Because I want to show you the probability distribution, the joint probability distribution P of x C1 and joint probability distribution P of x C2. And from that probability distribution, I'll show you where exactly would the decision boundary come in, right? Let us say the P of x C2, this one, this probability distribution, let us say it looks something like this. That is, starts like this, goes like this. Let's say it comes like this and something like this. Okay, this is the probability distribution of P of x C1. I'll mark it as P of x C1, x C1. Let us now draw P of x C2. I'll take a different color. I'll take red, and I'm drawing P of x C2. Let's say P of x C2 is something like this, and let's say it comes like this and goes over and then comes down. Let's say something like this. This is P of x C2. Okay, I'll mark it as P of x C2, P of x C2. So here you have two different probability distribution. One is of P of x C1 and the other of P of x C2. And let us say my decision boundary is presently here, somewhere over here. Let's say this is my decision boundary for now. At this point, I'll call this as x cap. Okay, x cap. This is my decision boundary. If I draw decision boundary here, what will be the situation? How many points will be classified correctly and how many points will be misclassified? Let us see that. I'll take a different color and mark it. Let us say I'm taking green. Okay. So let us say this is my x cap. In this case, if my point I am trying to classify to C1 and C2, which all areas do you think will classify it correctly and which all areas do you think will classify it wrongly? What about this area? This area, will it classify correctly or there is a probability for error? There is a probability for error, right? Why? Because this comes under the distribution P of xc1 and also it is coming under xc2, which means it is coming under both the curves and hence in this area there are good chances of misclassification. Similarly, if you take this area, what about this area? This area also has the same characteristic, that is it comes under the curve of P of xc2 and also the curve of P of xc1, which means again here also misclassification chances are there. So till this point you're clear that if a point belongs to this area or this area, there can be a misclassification, which means you will make a mistake over there. What about this area? This is what I am interested in discussing about. As of now, this area is under the curve P of xc2, right? Under the curve P of xc2. But you are marking it as C1. Why are you marking it as C1? Because your decision boundary is this, right? This x cap is your decision boundary. What will you do? Whatever is in this side of decision boundary, all these parts you will mark as R1. Whatever is in the right side of decision boundary, all these points you will mark as R2. But if you consider this area, these points actually belong to which class? R2, because it is under the curve P of xc2. Okay, P of xc2 curve has it covered and xc1 curve doesn't have it covered, which means these points clearly belong to C2 class, but you are having it as R1. So what do you want to do? You should actually mark it as R2. So what do you have to do for this? This decision boundary x cap, you have to move from here to here. Okay, if you move it to here, if you move it to this point, what will happen? Let us mark it as x0. If I move this decision boundary to this point, this area, this will go off, that is this misclassification. This area is no more misclassified because now these things are all marked as R2. Whatever is to the right of this decision boundary are marked as R2. Whatever is to the left of the decision boundary, these are marked as R1. In this case, this particular area, this is correctly marked as R2 because now it comes under P of xc2, which you are marking as R2 because your decision boundary is here, which means you now saved these points from being wrongly classified. Oh, I removed that as well. Okay, I'll redraw it. It was something like this. Okay. So this is how you want to identify. That is by identifying the posterior and identifying the decision boundary. What is your model learning? Your model is learning to identify the correct decision boundary. Let us say it starts somewhere here. It will identify that this is the actual decision boundary. So with time it will identify this is the right decision boundary to make. It will come to this point. Once it comes to this point, misclassification rate is the minimum. Why am I saying this is the minimum? Because see, this area no one can save because this area, it is coming under both the curves. This is under curve P of xc1 and also P of xc2, which means whatever comes under this area, which is under both the curves, there is a chance of misclassification and you can't help. What can you do with the decision boundary? You can try to draw the decision boundary at the point where you can minimize it. That is all the points which you can classify as R1 and R2 clearly, they should be classified correctly. That is the idea. So with this graphical understanding, you should be able to imagine how it works inside, right?